Welcome to the office. We want to take a look at a couple of examples where we compute the kernel of some homomorphisms. The first homomorphism that we want to consider is the mapping phi from the integers to Z10, where phi of 1 is 6. All right, so in this example, we want to remember a couple of things. First, repeated addition is written as multiplication, right? So if there's n terms, this is n times 1. And we're going to use that fact here. Yep, that's what we want to use here. Okay, fantastic. It's right. It's the idea of powers. So in the last video, we said that phi of a to the n is equal to phi of a to the n. In this particular example, because we're using addition as our notation, what we're saying is that phi of n times a is equal to n times phi of a, because we're using addition as our operation instead of multiplication. Okay, so we're going to use these notations to help us in determining what the kernel of phi is. So by definition, the kernel of phi is equal to all of the elements x that are in the domain of the mapping, such that phi of x gives us the identity. Now, the identity in Z10 is 0, so that's what we're looking for. If you're curious as to what mapping we're working with here, this is not necessarily the natural homomorphism that we talked about in a previous example, and that's because this is certainly not the remainder when the division algorithm is applied. We are using this to define our homomorphism with this understanding, much like we defined isomorphisms by the image of generators as well. All right, so under what circumstances is phi of x equal to 0? Right, so we're going to start to rewrite what we have going on here. So it's all of the integers such that now we have that the image of 1 is 6. So phi of n times a, x is x times 1. So we can understand this to be not phi of, but the image of x times 1 is x times 6. So we're looking for the things x times 6 that are congruent to 0 modulo 10, because we're working in Z10. But in order for it to be congruent to 0 mod 10, it has to result in a multiple of 10. So x times 6, or 6x, is equal to 10k for some integer k. Now notice that these both have a common factor of 2. So we're looking for integers such that 3 times that integer is equal to 5 times something. Now we agree that 3 does not divide 5, 5 does not divide 3. Okay, so in order for us to have that 3x is equal to 5k, we have to have that k, for example, has to have a factor of 3. That's fine. But in particular, the value of x has to have a factor of 5. So we have to have that 5 divides x in this case. Now this maybe isn't the most obvious step here, moving from this line to that one, because the usual representation of divides would say that x is equal to 5 times an integer. And the thing is in order for this to be true, we have to have that 5 divides x, because there's no other factor of 5 over on this side. Okay, so if we write out the prime factorization, so I'm okay with us making the jump from here to here. If you have any concerns about it, let me know. But all of the integers such that 5 divides the integer, we can simply write as 5z. All the multiples of 5. So the kernel of phi is just 5z in this case, and that's it. That's all we were looking for. We're going to use the same approach to find the kernel of this mapping as well. The mapping from z cross z, the direct product of z with itself, into S10, okay? S10 here, not Z10, but S10, where phi of 1, 0 is 3, 5, 2, 4, and phi of 0, 1 is 1, 7, 6, 10, 8, 9. All right. We want to notice here, that the order of phi of 1, 0 is equal to 2. We should be familiar with that. And that the order of phi of 0, 1 is equal to 4. We should be familiar with that as well. These both are cycles of length 2. Therefore, they have order 2, and the least common multiple of 2 and 2 is 2. Order 2, order 4, least common multiple of 2 and 4 is 4. So that's what we get for the orders of those elements. So what we're interested in having happen, to find the kernel of phi, we are looking at all of the elements A, B, in Z cross Z, the direct product there, such that phi of AB is equal to 1. So this just represents that 1 is a stationary element. It's a fixed element. It doesn't go anywhere. And everything that's not listed is also a fixed element. So everything is fixed. That is our identity element in S10. So let's start working through what it looks like to write this in a way that's a little bit more enlightening. So how can I rewrite this? Well, I can recognize that a B I can write as, now here, this is where we need to be very careful. What we're going to recognize is that 1, 0, and 0, 1 are the generators of Z cross Z. What they map to are disjoint. And since they're disjoint cycles permute or commute, right? They commute. So we actually get a nice commutativity here. So AB we can think of as, in Z cross Z, it's addition. This would be A0 plus 0 B, and that's fine. But that gives us that the image of A0 plus 0B is equal to phi of 1, 0 raised to the A power and times phi of 0B raised to the, 0, 1 raised to the B power. So since we have this, we want to utilize that fact. We are interested in phi of 1, 0 to the A, phi of 0, 1 to the B, giving us that identity element. So we're just looking for orders, right? So exponents here that are going to result in the identity. So all we have to do is take multiples of the order of this element and multiples of the order of this element. So A just needs to be a multiple of 2, and B just needs to be a multiple of 4. So I need to have that 2 divides A, and 4 divides B. A is a multiple of 2, B is a multiple of 4. It's a nice way to write it, which allows us to recognize that we're looking for the things A, B, where A comes from 2z and B comes from 4z. So this is just 2z cross 4z. Cool. That is the kernel. So this is kind of a fun, kind of a couple of fun examples here. Let me know if you have any questions. You should expect to see similar questions to approach in your homework. So I'll see you guys back in the office in just a little bit for actually another example, not computing a kernel, but a useful example in terms of trying to create homomorphisms. So I'll see you guys back here in the office in just a moment.